Let us now examine some software tools for controls applications. There are several softwares available. One of the most popular is MATLAB. Almost everybody would have heard of this and even used it. Another very popular software environment is Python. It also has control toolbox modules which we can leverage and use for our control applications. A third software, Octave, is another popular and very powerful programming environment which also has several tools and toolboxes that will help for control applications. Octave has a programming syntax very similar to MATLAB, and people using MATLAB will definitely be very comfortable with the Octave environment too. MATLAB is proprietary in nature, whereas Python and Octave are open source tools. Any one of these can be used for our controls applications for analyzing and synthesis of controllers. For the purpose of this lecture, I will scope it such that we will be examining and learning only open source tools. Of course, all these applications can be done on MATLAB too, but I would like to focus and concentrate on the open source tools, especially Python and Octave. So let us try to learn and understand how we would do controls applications, analyzing the systems and also synthesizing the systems using tools that are available in Python and Octave. So now let us take up Python first. So Python for controls. What do you need? You will need Python, of course. You need to have Python on your system. So if you are using Linux, Python is inbuilt into your distribution. It is available, and most of the cases you will have now Python 3+. If it is Mac or Windows, you may have to install onto your system. I am using a Fedora Linux distribution on my desktop, so Python is readily available. Next, you need an IDE, Integrated Development Environment. You could write your programs using any text editor, but it will be advantageous to use the IDE because you will have color highlights of the syntax. I will use Jupyter Notes. Jupyter Notes is an interesting IDE. As you will see, as we go along, you will see that it's quite powerful. It is browser based, and when you install Jupyter Notes, you will also be installing another IDE called IPython. IPython is an interactive Python interface which works from the command line, and it is a kind of a simplistic, minimalistic IDE, very helpful and quite powerful. So Jupyter Notes leverages this IPython interface. And third, what you need is the Python control toolbox module. So the Python's control module needs to be installed onto your machine. So all these three needs to be there, and then we can go ahead start analyzing our control systems and even synthesizing the control. So let us go through the steps of setting up the machine for Python controls application first, and then later on look at Octave and see its installation and application. So first let us try to see how we go about installing Python related softwares. On my desktop I have Fedora 35 Linux distribution. Python is built into the distribution, so I don't have to separately install Python. However, I need to install few other packages for my Jupyter to work. So let me start installing them. I will open this command terminal window, and let us do it through the commands. So I will use pip, Python's pip install command, and install nbconvert user. You can use this syntax, so you will see that it gets installed onto my system. I will clear the terminal window again, then install the next one. I will again use the pip command, pip install nbconvert web PDF. These are useful for taking printouts after you have used the Jupyter nodes. Let me clear again. So I am doing this in this sequence: pip install PDF template. So they get installed. Next I will install 3 packages, Python modules, which are very useful for our control applications. Again I will do pip install numpy. If it is not already installed, in some of the distribution will be installed, but it will indicate to us if it is installed. We see that it is already installed. Next, another distribution that I would like to have, install matplotlib. This is another module which will be very useful. If it is not installed, install it. And then let me install one more package, pip install the control toolbox. This is very useful and very important. This has to be there if you have to use control applications on Python. So let us install that one. So done, that is installed, and I will do one DNF install of pandoc. Once that is installed, we can go ahead and install Jupyter. So it is successfully installed, and let me clear the screen, and we will now install Jupyter. It's done through pip install. Look at the spelling, it is not G-U-P-I-T-E-R, it is G-U-P-Y-T-E-R, and we will install that. So Jupyter is getting installed, and after it is installed, we will be ready to use Jupyter. Done. So we have all the relevant software packages installed, and now what I will do is I will just show you that in the applications package Jupyter would be installed. Let me show you the icon in the applications window. The Jupyter notebook icon is like this. So if you click on this, it will open up the browser, and one of the tabs, the browser, you will see Jupyter showing up, and then it will show you the local folders on your machine, on your desktop. So this is the local folder system which is there on my desktop, and then I can open a file from here and start using Jupyter. We will do that shortly. I will store the examples that I do in this own cloud directory. I will click, it shows the various folders that are there in the own cloud directory. I have created an empty directory, control examples here. I click on that, you will see that nothing is there. So this is where we will store all the examples that we do now with Python. So here on the user interface, you see that there is a new button here. Okay, I can open a new file. Okay, a new file where we can have an interactive Python code incorporated. So you see that this is created, and you have various action buttons here. And look at this one. This is saying that what you type is a code, or you can choose what you type is a markdown if it is just only going to be markdown, a piece of text. For example, now let me give it a title. So I have markdown, and let me make it bold. So let us say this is learning controls through Python. So this is what we have, the heading, and I can insert cell below. So I have a cell that is inserted here, and here I can type in the code. We will come to that. First, let us save this file. So I will save this file. I will save as. So I will save as in that same control example. So let me say I will give it a name as learning Python, and save. So saving is done, and you will see that it is available in that controls in this learning Python. This is the name of the file, and it will be available in the directory that we just created. We can in fact have a look at that. So I open the folder. You see the path on cloud controls examples. This is the directory that we are intending to save all the Python files, and this is the file that we have created. It has an extension .ipynb. So now going back to the Jupyter browser interface. Now let me close and halt. So this is, I'm closing the Python, halting. Let me go back to the home directory. You will see all the folders in the home directory. Now let us say that you want to begin a new session. So you will see this home directory, and I know that my files are in own cloud, and I place the files in control examples. And you see that this learning Python file is here, and I click on that, and the interactive Jupyter nodes comes into picture, and you can start typing the code here. So while you're typing the code, ensure that this is in this is indicating code here in this window, not markdown or any other item here. So if it is code, then Jupyter knows that what you are typing here is code, and it needs to compile, and it will compile and interactively show you the results. So this is what we want to do, and let us now start typing in the code. Let me start by giving a title to this example. I will choose markdown. Let me say example 01, transfer function and step response. Then I will insert another cell below, and here let me go to code. Yes, it is already in code. Let me start typing the Python code. Use comments so that they are descriptive. I will use a comment. Required modules to import. So I will be importing 3 modules. These 3 modules, NumPy, Matplotlib and control, will be almost always required in any controls related script. So this is a constant, so you can safely put these 3 modules in most of your scripts. Import NumPy, and I will name it as NP, means that NP is a short form for NumPy, so that in the code when I am typing I don't have to type the entire NumPy. I can just type it by the symbolic renaming, which is NP. Then I will import Matplotlib, the PyPlot module, and I will call it as PLT. Then import control. So we also loaded this module through pip, if you recall, and I will call it as CLT. So this forms the 3 modules that I am going to call. Then let us define a transfer function. Define the transfer function. So how do we define the transfer function? So at this point, let me go back to the whiteboard and let us see how a transfer function looks, and then come back again here to this code. Let me consider a transfer function g of s, a second order transfer function. So let me say the numerator is 1 and the denominator has 2 poles, so it's a second order equation, s square plus 0.5s plus 2. So some arbitrary transfer function. It has 2 poles, and we can say that it has a numerator polynomial in a generic sense, num of s, and a denominator polynomial den of s. So what are the numerator polynomial and denominator polynomial? In Octave, or probably even in MATLAB, you will write it as the coefficients of the polynomial in s, or coefficients of the polynomial in any particular variable. Even in Python, you will do the same thing. The numerator polynomial, the coefficient is of the numerator of s to the power of 0 is 1, so there is only one term, so you use that. Then for the denominator, so the denominator polynomial will have 3 terms: the coefficient of s square, coefficient of s to the power of 1, coefficient of s to the power of 0. So they come in this fashion. So this is s to the power of 0 coefficient 2, as you see here. 0.5 is the coefficient of s to the power of 1, and 1 is the coefficient of the second order. Likewise, the numerator also, 1 is the coefficient of s to the power of 0. So this is how you would represent the numerator and the denominator polynomials of a transfer function. So if you take the block having input and output, gs is the transfer function. Let us say we would like to incorporate this particular transfer function, and at the input, let us say we give a unit step, and what will be the output? Then we call it as a step response. So being a second order transfer function, you will get a kind of an underdamped response like this. So let us try to see if we can implement this transfer function and see a response to a unit step input. Okay, so this is what we would like to do in our code. And let us, so we learned the Python scripting for controls by examples. So that's what we are going to do. So let me go back to Jupyter Notes. Let me type in the numerator polynomial. Then I type in the denominator polynomial. So we had 1, 0.5 and 2 like this. Coefficients of s, powers of s. And then we use this numerator and denominator polynomial, combine them into a transfer function. So a system continuous domain, and we will use the CTL, the control toolbox, TF, and then state the numerator polynomial and the denominator polynomial. Now this sysc is nothing but the transfer function that we have defined. So let us print it out. Print sysc. So this is the definition of the transfer function. So if you run this, let us say I run this particular cell, which is highlighted marked. So run the cell. So if I run the cell, you see that it executes and the result is displayed. So what have we asked? We have displayed print. We have used the print function to display SYSC, system C. So it is nothing but 1 by s square plus 0.5 s plus 2, and this is expected because we have selected the polynomial as such. So next, the run creates another blank cell here. You can cut it out, not needed right now. We are sticking to just only one cell, and continue forward. So let us now, we want to see the step response, so we need to set the time axis. So let us set the time axis. Set the time axis, which is the x-axis range, and see the step response. So this we need to do. T, the time axis, x-axis is equal to, let me use the numpy, np, linspace function, the linspace function in numpy module. So I can give the starting value of the time x-axis 0 seconds up to the ending time, which is 50. And then you need to give one more parameter, the number of points. How many number of points you want from 0 to 50? So let us say 100. So what this line means is that a time vector t is generated, linearly spaced points from 0 to 50, and there are 100 points. And then we will use the control toolbox and use the step response function. And step response function, we are passing two parameters. We are passing the transfer function, which is sysc, and we are passing the x-axis time vector. So we need to plot the step response for this time vector and for this given transfer function g of s, which is inbuilt into this sysc. And after having done the step response function, the control toolbox, it will put the output. Tx is the x-axis value and y is the response function, the step response function. Yes, the step response has been calculated. And next we need to see the result. Right now we will not be able to see the result, so plot. Let us plot the results. So if I say plot, PLT, the MATLAB's matplotlib module is taken, and I will use the plot command, say tx comma y. So the x-axis and the y-axis. So I plot this. So this is the plot command. So unless you say show the plot, it will not show it on the workspace area. So show. That's Python syntax. So now this particular cell, let us run it, and you will see that okay, it has executed this print sys, displayed that here, and then it has displayed here the plot, the step response. So you see this is the step response. You see that it is settling at around 0.5. It is expected because this transfer function, if you take the steady state as s tends to 0, 1 by 2, it will finally, the transfer function will settle to 1 by 2, 0.5. So if you are giving a unit step, the output will be multiplied by 0.5. So you will see that steady state is at 0.5. So result is pretty well as expected. So let us try to add some more thing to complete. So here you see this plot. Okay, I will just remove this cell that is created, and I will go back to this plot statement. So right now it has plotted the response. Let me give grid. So what do we do? I will plot. I will use that PLT tool module, and I'll say grid. Then run again. So you will see that the grid appears at this point. And something more, you can add more information. You can include x label, plot dot x label. So let us say x label is nothing but time, seconds. Then I will also add the y label, plt.y label. The y label I will call it as magnitude. And also I would like to add one more thing, plt.title for this response. So let's say I will call it as step response. Show. So you will see that all these things should get incorporated. Now time axis label, which is time as magnitude, will come in here, and the step response title for this entire response. So let us execute, run it. So run. So you see this step response, magnitude, time, labeling, and the grid and the response all put together. So you see that as the first step we have learned two things: how to make a transfer function and how to plot the results, how to set the time axis and then plot the results. So this is the first step, the first example, and we will try to improve on this. Now let us do another example, and probably we can call this as example 2, and let us learn about discrete transfer function and discrete step response plot. So let us try this, and I will insert a cell below this and do the code. Okay. So you see that here I have not changed it to markdown. That should be markdown, and this is the code. So let me start with this basic draft here. So let me take up to this point. Let me take this. I will copy and I will paste it here. So in this cell, I have the required module the same. I am having numpy named as np, matplotlib.pyplot named as plt, control named as ctl, and I am taking the same transfer function, same continuous domain transfer function, and sysc is the continuous domain transfer function which we have seen last time. Now I will include this small change. So ts sampling time 0.5, let us say 0.5 second sampling time, and sysd discrete system. So sysc is the continuous system, sysd is the discrete system, and now I will call upon the control module ctl and let us sample the sample system function. So in the control module, the sample system function is used, and I will use the continuous domain system and the sampling time to convert it into a discrete domain system, which means it will be a z-plane system. So let us print it. Print sysd. So this should give us the discrete system. So here you see that print sysc will give you the continuous system, and this will give you the discrete system output. So let us run it and see. So I have chosen this cell, and then we are running that cell. You can choose cell, run cell. So it will run the cell, and you see that first one is the transfer function, which is the continuous domain transfer function. It has printed 1 by s square plus 0.5 s plus 2. It is the same. And the following that, the transfer function is the z-plane transfer function. You have 1, 0, and the second order denominator having 2 poles in the z-plane. So that is sysd, and with sampling time or delta t of 0.5. So that's what we have used. So probably we could say, you can say 0.2. If you say sampling time of 0.2, you can again rerun the cell. So it is with a sampling time of 0.2. This is your discrete transfer function. So now let us do the next step, plotting. So we will do that. So I will set up the time axis and see the step response. So I will set up the time axis slightly different. If you look previously, we had set it up using the linspace function. So in the linspace function, you have control on the starting value and you have control on the ending value. You can precisely specify the starting and the ending value, extremities, but you don't have much control on the delta t, the sampling time. You specify only the number of points. Okay, the one that I am going to use now, so t equals, now I will use the np numpy's arrange function, arrange or a range 0 to, so let me take 20, and ts now is the sample time. So it will go from 0 to 20 in steps of ts. So this is what it means, and this gives you control on the step time also, so which is very convenient for our discrete responses. Then after that, we take the sample system. So I will again use the control step response, and I will use this D, discrete, and the time that we have now set up. So this will give you the response. Then I will follow it up with plotting. So what did we do for plotting? Plot the results. Plot. Now instead of, okay, I could use plot. I will use plot tx comma y. Okay. I will use again the plot module, but I will call another function called step. Tx comma y, same thing. So what does this do? Plot is a smooth function. You have the points, discrete points here. It will do an interpolation and it will give you a smooth response. Step is the interpolation which is done at every TS interval. Sorry, not interpolation, the sample that is being done at every TS interval, and it will give you the sampled waveform. So that's why step is useful. So if I do that and then say PLT show. So now let us run this. Let us run this cell. So you see that both are plotted. So you see that you have the continuous waveform that is coming from the plot, and also the stepped version at every 0.2 seconds TS sample time. So let us probably make it a bit more visually effective while seeing the 0.5, so that you space it out. I will again rerun this. So you will see that this is at sample time 0.5, so that you can see that the stepped nature of the sampled waveform, sampling at 0.5 seconds. So this is plotting and seeing the you have the discrete transfer function, and you can also see the discrete output. One other thing that probably I can show here is subplotting. You have here two waveforms. Here two waveforms you're seeing on the same plot. It would also be nice to know that there is another method. Okay, what I will do, I will comment this out. So this is not there. Let me use subplot. So I will use the plot module and subplot. You would probably have used subplot in MATLAB or Octave. So this is, there are two plots, and this is 1, 1 plot coordinate. So you have plot, and then I will plot this t comma y, tx comma y. So this is my first plot, and plot, subplot, and of the second plot I will use plot step tx comma y. So this will give you two plots, two subplots, and you can see it in this fashion, like this. So you have two subplots, you have the same x-axis, and the y-axis can be different. And then you can give all the other, so you see here what we did: grid, x label, y label, step response. So let me copy this, copy, and let me use it here. I will use this here. So time axis, I will retain it. Magnitude, step response, we could probably call this a step response. Then here also we have this grid, time, magnitude, and the step response. This is discrete. Then you run the cell or run the cell. So you have this grid and you have the step response. Yeah, both the titles, they are kind of causing a problem with the x-axis ticks. So what you can do is remove this and make that as discrete step responses, and this will be much more pleasing to look at. Yes, your discrete step responses, magnitude, time axis, all this. So this is plotting discrete step response and also getting the transfer function in the discrete domain. Let us do one more example. This time we will do it in the frequency domain. So let me first insert a cell below, and I will take markdown and say this is example 03. So we will say example of Bode plot. Bode plot example, and let us run this. So now let me put in the code. Let me take the same transfer function and see how we can do a Bode plot for that system. So I will take exactly the same transfer function as we had taken before. Just copy that and paste. So we have the same modules, NumPy, Matplotlib, and control, and the same transfer function sysc. So now let me define the x-axis. X-axis now is the frequency, the omega axis, also w axis in radians, and let us use NumPy np.log space. So the x-axis can go logarithmically from 10 to the power of -1 to 10 to the power of 2, like this. So this is the syntax for that. Logarithmically spaced radian axis, and then we are ready to develop the plot, the frequency response plot. So we would like to have the magnitude, phase, and the omega of the x-axis. And let us call CTL, the control toolbox, and in the control toolbox the Bode function. So the Bode function takes the system and you give the omega axis vector, then you can give some options. db is true, plot is false. We will do plotting externally with our subplots. So this forms the frequency response part. Then let us now plot the results. So for plotting the results, I will use the subplots. So I will take the plt matplotlib module subplot. So let us have two plots. One is 1, 1, and then plot what? So I would like to plot a semi-log x, that is along the x direction, along the x axis we want logarithmic, and along the y direction normal plotting, linear plotting. So semi-log x, we give the omega axis, x axis, and the magnitude, and then we can ask to plot the grid. And when you, okay, I will just put it to this fashion we are familiar with. Then plot the x label and the y label. So I will just put the y label, magnitude. Okay, so we have this. So you can add all the other items, so like x label and such, and even title. So plot, subplot 2, 2. So this is the second one below, bottom. Plot semi-log x. So omega versus phase angle in radians, and plot the grid and plot the y label. Y label is phase angle in radians. Then plot show. So you now have the script in place. Let us run the script and see what happens. So let us run this script. So you see the plot. This is the Bode plot. Frequency response. The x-axis is frequency. From 10 to the power of -1, we had given the omega generation logarithmically spaced. -1, 2 means that 10 to the power of -1 to 10 to the power of 2. So 10 to the power of -1 to 10 square radians. And you have the magnitude on the top plot and the phase angle in radians in the bottom plot. It goes up to pi minus pi, which is again evident because this is a second order system. But the grid is not okay. It is the linear spaced grid. So let us say that the grid, we want both on one direction linear, on the y-axis we want linear, on the x-axis we want logarithmically spaced. So you say both. Same here. Which type of grid? We want both. So this will, then here you can say title and say Bode plots, and then again you run the cells and you see that you get the Bode plots where the x-axis grid spacing is logarithmic and the y-axis is linear space. So this is semi-log. So in this way you can get, for the same transfer function, the Bode plot also. You can also get the Bode plot of the discretized. So let us say you are now get a sample time. So let me take the sample time as 0.3 going by, okay, let us say 0.1, and then we say sys d. I will call the control toolbox and sample system, pass the continuous system and the sample time. So now I have the discrete system also, and then when you are doing the Bode plot, I can do the Bode plot for the discrete system. So I just want to show how the plot looks like look almost similar because we are well within the Nyquist frequency. So I will run. So we are actually not well within the Nyquist frequency. So you see that the bandwidth we should stay lower than this value here, the frequency of 10, 20, 30, less than 30 radians. So let me decrease the sample time to 0.01. Anyway, I'm doing this by trial and error just so that I wanted to show you this error, that you see that it gives you a message saying that the sample time chosen is not proper, that you are having some parts of the plots which are above the Nyquist frequency and that is not reliable, okay, because of the aliasing effect. So if I reduce this sample time and then run it, so you will see that the whole entire Bode plot is within well within your Nyquist frequency. So this is the third example where we looked at the Bode plot or the frequency domain plots, with the x-axis being the frequency domain, being the frequency in radians. And the previous two examples were time domain plots where the x-axis was time vector. So before closing for this class, I will just like to show that all these things that we have done, Jupyter Notes has the facility that you can save it and save it as PDF file or save it as HTML file, and which will be ready for documentation. In fact, you can add a lot of documentation explaining the scripts or also the theory behind it, and then you have a complete documentation. So you could go here, save. So I will save it into the same learning Python file. So I'm saving it, overwrite that, yes. I can also download it as a PDF. Now that is very interesting. So if you go to download as, there are several options he gives. Okay. One, let's say HTML, you can download it as HTML, and then when I see the HTML file, complete HTML file with all the scripts, explanations and the output results will get displayed. So I can download it as a PDF, LaTeX PDF. So in fact, to do this download as a PDF, we need to install Pandoc. You recall that right at the beginning we did a sudo dnf install Pandoc, that is necessary. So you can install that and then your downloading to PDF will be ready. You see that PDF is available. I can click on that and then you have the entire PDF file. Learning Python, this was generated at this time. All these things come as a very nicely well made LaTeX document along with the scripts and the output results. So this becomes a ready to use notes. You can download it and share it with others too. So with this I will conclude this class, and probably in the next class we can take up further examples of Python for controls.